Okay, now at this point we've talked about angles, we've defined what they are, we've talked about how to measure them, what that means, sort of. And we've talked a little bit about sectors and how we take a slice out of this thing, treat it like a pie. And in doing so, we've figured out how to look at something that looks like this. So I take a piece of this, some angle theta, it's going to have a radius r, and the distance I would walk around that outside, we'll call that s. And one thing we haven't talked about is if we keep this in the context of a circle, it tells me, it defines a point on the outside of the circle. And we'll talk about that coordinate as having an x and a y value. Okay? And one of the things to note is that the distance from this point to the origin is going to be the radius r by definition. So every point on this circle has an extra constraint on it. Okay? And it's going to turn out we can talk about these extra constraints only in terms of this angle theta. The question is why can we do that? So what I'm going to do is I'm going to first talk about what this angle theta really tells us about any point on the edge of this circle. I'm going to define some things called trigonometric functions, and then we'll play around with that. Okay? All right, so let me redraw this. Let me come over here. And the first thing I want to know is this idea of just looking at coordinates on the edge of the circle, is this a well-defined process? So think about it this way. Suppose I've got a circle of radius r, and I've got a point on here given by xy. Okay? And this is given by some angle theta. The thing to note, if I were to take an even bigger circle, like this, perfectly centered, and extend this out and look at this point right there, let's call this point u and v. Okay? Is there a relationship between x and y and u and v? Okay, and the answer is going to be yes. And the reason is notice we've just formed a triangle right there. There's also this triangle right there. So let me break this out. I've got this big triangle, angle theta there. This is a right triangle, because the way I defined it. This is the point uv, so that means the distance from here to here is u, the distance from here to here is v, but I've also got this smaller triangle right here, which is also a right triangle. That coordinate is xy, so that means the distance from here to here is x, and the distance from here to here is y. And now here's a key thing. I called this distance here r. This is another circle, a bigger circle. Let me suppose it has a radius capital R. And notice we have two similar triangles. Okay. That means these ratios are going to be constant, okay, or they're going to be similar in terms of how I look at x over r. So this divided by that is going to be the distance here divided by capital R. This height here divided by that hypotenuse is going to be this height divided by that hypotenuse. And lastly, y divided by x is going to be the same thing as the ratio of that distance divided by that distance, which is v divided by u. Okay? So the key thing to recognize here is that no matter what size circle I use, these ratios are the same. Right? They don't change based on the size of the circle. They only depend on where they're at on this ray, and they only depend on this angle theta. Okay? And likewise, theta is going to depend on the radius and the length of that sector. But because these are along this same ray, I can start thinking about this only in terms of this angle theta. Okay? So if I defined these ratios in terms of theta, I'm just going to make a function up. These are going to be true for any size circles, and these ratios are a well-defined quantity. Okay? So I'm going to make up some names for these, and as usual, we're going to try to make these as confusing as possible. Okay, so here's the definition. This ratio, the horizontal divided by the distance, we're going to call this the cosine. This vertical distance divided by the radius, we're going to call that the sine. Notice we spell them differently than the way we abbreviate them because it's more confusing. And then finally, this ratio, the rise over the run, we're going to call that the tangent. Okay, these are just definitions, and the reason why we can define these is because these ratios are well defined for any circle. Okay. So let's take a look at this. First thing to notice, everything here I did was in the first quadrant. Okay. It's going to turn out that that's not a big restriction. So if I have a point here, x, y, and it's say over the second, third, or fourth quadrant, I can still make this same definition where cosine of theta is x over r, sine of theta equals y over r, and tangent of theta is y over x. Moreover, as long as r is a positive number, this is going to work no matter what. And what I want to do is I want to figure out is there a single circle that I can use that can be used in any case and be able to think about these things. And the easiest thing to use is the circle of radius 1. So the circle of radius 1 is we're going to call that the unit circle, unit for the radius being 1. And in that case, what do we have? We're going to have that the cosine of theta is just the x-coordinate of that point. The sine theta is going to be the y. And the tangent is not going to change because there's no r there. Okay? So if we're working with the unit circle, the radius is 1, this becomes just the x value of this coordinate, this becomes the y value, and this is still the ratio of the rise over the run. Okay? So let's stop and think about this new function. Okay. So this as a function, as my theta changes, the value of the cosine is going to change. And the same thing with sine. As the value of theta changes, it's going to change as well. So let's see, what do we have? If we're in the first quadrant, the cosine is going to be some point here. It's going to be the x value. That x value is going to be positive. The sine is going to be the y value. It's also going to be positive because it's up here. Right? So if I think of that as being this is my x and this is my y. So for any angle in the first quadrant, the cosine is positive, the sine is positive. I'm in the second quadrant. Now, my x value is negative, so the cosine is negative, but the sine is still positive. In the third quadrant, I have a point here. Now the x value is still negative, the y value is now negative, and then finally over here, right, if I have an angle that puts me over into the fourth quadrant, the cosine is the x value is positive, and the sine is negative. Okay. Finally, if I'm in here and I'm going around and my angle is increasing, so if I sweep out and my angle keeps getting bigger, my x value is getting smaller, so it's decreasing. Now if I start here and move up, the y value is increasing. Okay. Now as my angle sweeps through here and gets into the second quadrant, the cosine is still, the x value is still moving to the left, so it's still decreasing. Now the sine value, the y value is moving downwards. It's also decreasing. So I get into the third quadrant, let's see, so my x value is starting to move to the right, so now it's increasing, but the y value is moving downwards, so it's decreasing. And then finally in this fourth quadrant, it's moving around that way, the x value is moving to the right, it's increasing, and the y value is moving up, so it's increasing. So in terms of what is the sine or cosine in the first, second, third, or fourth quadrant, as it's sweeping up, cosine is positive, but the x value is decreasing. The sine value is positive, and it's increasing. Over here, as I sweep around this way, the x value is still moving to the left, so it's negative and decreasing. The sine value is still positive, it's above the x-axis, but it's decreasing. In the third quadrant, as I move around this way, the x value is moving to the right, it's still negative, but it's going to the right, so it's negative, increasing. The y value is moving downwards, and it's negative and decreasing. Fourth quadrant, as I move around this way, so as my theta increases here, the x value is still moving to the right, and it's now positive. The y value is still negative, it's below the x-axis, but it's getting bigger. It's going to go increase up to 0, so it's negative and increasing. Right, so let's look at a couple particular examples of some angles where we can figure this out. By the way, there's only a small number of angles that we can figure out the values of these. We usually have to approximate them, which means going to the calculator. And fortunately, your calculator has built-in functions to evaluate these angles. So let's just look at a couple, just to help us get a feel for how these things are defined. So let's think about these two. This one's going to be a little easier, so let me think about that one first. Okay, so pi over 2 is 1/4 of the way around. So it's going to be that point. And if I have the unit circle, this is going to be x equals 0 and y equals 1. So I immediately get that cosine of pi over 2 is the x value is 0, and the sine of pi over 2 is the y value is just 1. Okay. Now, if I look at pi over 4, it's going to be a little trickier. I'm going to have to think about this in terms of triangles. So here, I'm basically 1/8 of the way around, and my x and my y values are going to be the same because this is the y equals x line. Right? So if I think about this as the angle that's halfway between here and here, that line is y equals x. So I know that, and I've got this triangle, so maybe I can sort things out from this triangle. So I know that's x, and it's a unit circle, so I know that's 1. If I use the Pythagorean Theorem, I know that x squared plus x squared equals 1 squared. So 2x squared equals 1. X squared is 1/2. So x is the square root of 1/2. I've got to be careful, it's plus or minus. In this case, I know that I'm at this point right here. So it's going to be positive 1/2. And I already know that that's equal to the y value. So that automatically gives me that the cosine of pi over 4 is the square root of 1/2, and the sine of pi over 4 is the square root of 1/2. Okay, one last note. Coming back to this idea of looking at this as a triangle, we can say something in more general terms. So just any angle here. I pick this angle here, some angle theta. Okay. If I bring a line straight down to there, I get a right triangle. And I know the distance from here to here is my x value. My distance from here to here is my y value. And I know I'm working with a unit circle, so I know that's true. So I immediately get x squared plus y squared equals 1 squared. But from my definition, x is the cosine of theta, y is the sine of theta, and 1 squared just equals 1. Right? This is oftentimes referred to as the Pythagorean identity, because it comes straight from the Pythagorean identity.